Okay, so good afternoon, class. So medyo may ginagawang construction malapit sa amin. So, if may times na medyo mean, I guess siguro gawan na lang ako ng additional na or type out ko na lang something basta gawa natin ng para. Okay, so this is for the review for the LQ or the long quiz 1 for EEE 153 this first semester of school year 2020-2021. So the coverage of the long quiz covers the is yung first 5 weeks of class. So that is the introduction of concepts or more or less a definition of terms, and then the MIPS instruction set architecture, and then from a single cycle to a pipeline data path of the MIPS architecture. So for the first one, I think kaya naman ng mag-go over na lang kayo sa mga materials, more or less definitions lang naman sila. So basa-basa na lang sa slide. So for the MIPS instruction set architecture, gusto kong i-build up yung palang maging structure ng ating review. Parang papakita ako ng short review on the specific topic and then some sample problems afterwards. So for the single cycle data, for the MIPS architecture, may review kasi dito sa slides, which is I think more than enough as a quick reference ng mga ganap. So sa 32, meron tayong 32 registers kasi 32 kasi. So yung mga registers natin, may kanya-kanya silang usage by convention. Although, except for the 0 register, lahat sila ay pwedeng sulatan mo as the programmer. So ito, mga convention lang naman. So for example, si $80 or register number 1 is reserved for the assembler for pseudo instructions. So wag dapat siyang galawin. And then for registers 2 and 3, V0 and V1, usually ito yung ginagamit na register for results ng subroutines. So pagka, kunwari, in high-level programming, kunwari, yung function mo, may nire-return siya na value, dito na sa store sa register na yung return value ng isang subroutine or function. A0 to A3 naman yung arguments, so registers 4 to 7. So arguments, siya yung inputs mo doon sa inyong function or subroutine. And then, itong temporaries, mga temporary registers na pwede, parang medyo general purpose registers sila na pwede mo sulatan or and everything. Then si S0 to S7, 16 to 23 ay saved temporaries yung tawag yan. So parang general na variables yan, pero it is assumed na yung sa function, hindi nila pwedeng galawin yung naman na S0 to S7 or sa mga subroutines. So for functions and subroutines, ang temporaries lang usually yung ginagamit. And then meron tayong global pointer when it comes to memory. And then yung stack pointer, pag naglalagay tayo sa stack, frame pointer related din siya sa memory. And then return address. So if nag-jump tayo, nag-jump instructions tayo using our para tumawag ng mga subroutines, usually dyan sa RA natin nilalagay yung result. So another part ng MIPS 32 architecture ay about sa memory addressing. Tapat ko yung mic sa bibig. So in MIPS 32 memory addressing, memory addresses are 32 bits. So each cell in memory it has a 32-bit na address, and then byte addressable tayo, which means an address corresponds to some 8-bit na data. So isang memory address, that is 8 bits of data. And then pwede tayong maging little or big end yan. So always double check your specifications nung ginagamit yung device. And then tinatawag na words are 32 bits and instructions are 32 bits long din. So yung 32 registers din natin ay 32 bits long. So yung mga instructions natin in memory, pagka ang instructions na-convert siya into binary, and then yung binary na information na yun yung sinostore natin sa memory. So for example, ang command or instruction add V0, A0, A1, ma-convert siya to the add operation, tapos yung specific numbers ng registers, which is 2, 4, and 5. And then pag kinonvert mo yun into its binary equivalent, it's 00851020. And ayun, for example, magsa-start yung instructions natin at address 0, doon isusulat si first code. And then you'll notice na yung first address natin is 0, ang next address natin is 4, kasi meron tayong ang kada isang bit ng address ay 8 bits long. And then, since ang isang instruction ay 32 bits long, ang next instruction ay makikita 4 addresses later after nung previous na instruction. So, yun na naman. Then, next is, ayun, ang encoding natin, usually, for all instructions, lahat ng first 6 bits ay for the opcode or anong ginagawa no certain instruction na yun. And then meron tayong tatlong general types or formats ng instruction. So yung first one is R-type, which is yung parang operands natin are all registers. So meron tayong source register, meron tayong first register, second register, at saka destination register result no operation. Tapos meron din shift amount and another 6 bits dito related dun sa function. So yung shift amount ginagamit mo to usually pag sa shift operations, I think. And ayun, for I-type naman, so ang I, which means immediate, and then immediate is something na immediately na alam ng processor, which is constant basically. So pag naglagay ka ng straightforward number doon sa iyong instruction, doon siya mapupunta sa immediate na field. And then, ayun, meron lang tayong isang source na register and then isang source na register, isang destination na register. And then yung J-type naman is ayun, 26-bit immediate yun nakalagay sa kanya. And usually it's used for jump type operations, and yung 26-bit immediate na to is yung amount na i-jump noong ating instructions. So ayun, ito yung sample list of instructions lang, and ito rin yung mga functions na covered dito sa slide set na to. So as you can see here, sa first 4 R-type sila. Yung opcode nila lahat is 0000. And then yung sa function field naman nila is doon sila nag-iiba. So for the add instruction, yung function code niya is ito. So ito yung binary, and equivalent niya in decimal. So this is 32, subtraction is 34, and is 36 or is 37. And then dito naman sa add I, so may immediate siya. So yung immediate na nakalagay doon sa instruction, dito siya mapupunta. And then yung source and destination registers dito. And then yung jump naman, ayun, so yung nakalagay lang sa operation itself is yung address niya. So yeah, I think yun naman yung mostly about sa MIPS instructions. So let's have a few questions which I lifted from the previous offering ng 153. So for this first question, complete the snippet of a MIPS assembly language instruction that increments a counter. So si counter ay ito, may label na counter, and parang siya yung placeholder natin for the address in memory ng counter na variable na yun. So, ayun. We will assume that the counter is a label of an integer stored in the main memory. So, when your code snippet completes, the value in memory should be appropriately updated. So, yung first line, I guess parang i-decode natin siya. So, ang ginagawa niya lang is tinostore niya kay T0 yung nakalagay sa memory counter. So, load word. So, pagka kumuha tayo ng data from our memory, it takes one command to store it to a register. So after natin i-load yung word, ang gusto natin mangyari is ma-increment yung laman ni counter. Ayun nga pala, ang gusto natin mangyari talaga is ma-increment yung laman ni counter. Pero si CPU natin, hindi niya kayang baguhin directly si value ni counter. Kasi sa registers lang siya pwede magsulat. So yung una natin ginawa is tinorm muna natin sa register yung laman ni counter. So yung next na gagawin natin dito is increment natin yung laman nung nasa register. So that is add immediate doon kay T0 and mag-add tayo ng 1 na immediate. So, ayun. Ay, pwede ko palang. So, kung mag-increment tayo, mag-add tayo. Add I. Saan tayo mag-add? Kay T0. And then mag-add tayo ng 1 sa kanya para mag-increment siya. So, ayun. Ang next naman natin na kailangan gawin is, ayun, si T0 yung nag-update pero si counter yung gusto natin ma-update. So, kailangan natin isulat yung laman ni T0 kay counter. So we can accomplish that by using the save word na command. And then, ano yung isi-save mo? Si T0. And saan mo siya isi-save? Sa kay counter. Ayun, di ba? Ang galing naman ng gumawa ng slides. And ayun, so this is yung ating sagot for question 1. Then for question 2, so in the figure shown is copied from a PIC32 simulator output that is assembled and loaded. So ang question number 1 is, when the CPU fetches the first instruction in this code above, so that is yung code na move S6T0, what is the value of PC? So yung first line natin dito, ang pinaka-leftmost dito siya yung ating address ng ating instruction. Ito naman yung binary equivalent ng instruction, and ito yung actual na instruction in assembly. Ito yung tawag natin pseudo instruction na ginagawa ng assembler. So, ayan. Since yung nga sa first column yung address ng instruction, kakopyahin na natin tong 400090. Take note na lang sa number of 0. So, and then the second question, the second line of the figure includes the instruction SLT, or set if less than $1, $9, $8. So what are the names of the 3 registers used in this instruction in the same order? So pwede nating i-check yung ating reference. Open notes naman yung exam. So si $1 siya ay si $80. So dito nila. Yan. So si $9, if check natin siya si T0 to T7. So siguro yung pangalawa, T1. And then si T8 ay si register number 8, siya si T0 naman. So number 3, the last source instruction in the sequence is add I T0 T0 negative 1. So the resulting machine language instruction is ito, 2108 FFFF. So which part of this hexadecimal value represents negative 1? So ayun, so si add I na instruction is a I type na instruction. So yung first 6 plus 5 plus 5, so yung first 16 bits niya is for the input operands. So kung saan siya i-write at saan siya i-save, ay kung ano yung ano yung value na add natin and saan siya i-save. And then yung last 16 bits yung immediate na ina-add natin. So the last 16 bits ng ating instruction code is itong last 4 na F. So exactly naman, tama naman. Yun naman ang -1 pag tinose complement natin siya. Ayan. So hopefully okay pa yung medyo nakikipag-away ako sa labas. Okay. Question number 3. Okay, so given the contents of these registers, so si $S1 ay FFF000, and si S2, so medyo konting typo, so may simula yan. So 8DF3, E1, 6F. And ano ba yung result ng operation na to? So basically, end ko si S1 and si S2 and i-save ko yung result kay S3. So, well, sa mga sanay sa binary, obviously dapat yung sagot, tsaka sa bit masking, sanay alam nyo na dapat yung sagot. Pero ang longer way of doing it is convert natin pareho to binary kasi bitwise operation to, so we need to see the bits. So yung FFFF0000 is just puro 1 ang apat and then puro 0. And then dito naman sa baba, so si 8 ay 1000, si D ay 1101, and then si 4 ay 0100, and 0, si 3 naman ay 0011, and then so on and so forth. So para mag-bitwise na end, i-end lang natin lahat ng magkakatapat na digits. And then since end operation to, as long as 0 yung isang row, 0 na yung result. So yung latter half dito, di natin actually kailangan pansinin. And then as long as 1 yung isang side, ikokopya lang natin yung nasa other side. So ang result ng AND operation is actually the first 16 bits or the first 4 bytes, tama ba? 4 bytes na ating S1, which is 8D43. Pero note that si S3 ay 16-bit na, ay 32-bit na register. So kailangan pa nating ilagay yung huling apat na 0 to complete the 32 bits. Okay, next naman, question number 4. Consider the hex value 0x20030007 as representing one MIPS machine language instruction. So ano yung pangalan ng opcode or what is? So basically anong ibig sabihin ng instruction na to? So, of course, convert muna natin siya into binary para makita natin yung specific na bits. So, si 2 ay 0010, and then dalawang groups of zeros before yung 3 na 0011, and then puro zeros hanggang 7, so 0111. So, ang opcode natin, lagi naman siyang 6 bits. So, i-group natin yung first 6 bits dito. And then, meron naman tayong mga comprehensive reference, pero makikita natin dito si 001000 ay yung opcode natin for the add I instruction. So, yun na yung sagot sa tanong dito actually. Pero if gusto natin pang dahil extra tayo, pwede din natin, since alam natin na add I instruction siya, alam natin na yung next 5 bits or next 10 bits, yung 5 doon is RS, yung another 5 is RT. So, pwede rin natin makuha yun, and then yung immediate na ina-add natin. So, pwede natin silang in-group. So, yung first 6 si opcode, next 5 si RS, next 5 si RT, and then yung last 16 yung immediate. So, yung RS natin is 0. So, si source, so siya yung actually second operand. And then si RT, siya yung destination, which is $3. And then yung immediate natin is 7. So medyo magigets nyo kung bakit siya immediate kasi makita nyo dito na sa dulo ng ating operation code, we have a number 7. So immediately natin nakikita kung ano yung ina-add and hindi na kailangan pa mag-access ng registers. So yan, yun lang naman yung mga sample questions ko for regarding yung MIPS na instructions. Then, ayun, actually for the single cycle and multi-cycle data path, wala akong personal na materials. Pero meron naman dito meron pin-provide dito sa week 4. So medyo related naman kasi ang multi-cycle sa single cycle. Usually, kino-compare natin sila to each other. Pero yun, to give a short rundown kung paano yung single cycle and multi-cycle. Siguro yun, let's just define that yung ating data path is yung flow ng ating data to execute the instruction. And then usually meron tayong 5 steps dito whenever we try and execute an instruction. So yung first is, of course, kunin yung instruction from memory. So something to note lang is yung pagbabasa from memory is not a fast operation. Kaya usually, naglalagay tayo ng separate na time para lang dun sa pagbabasa from memory. Kaya yung registers natin, sila yung mga mas mabilis, pero limited amount lang siya to 32. So bakit hindi na lang natin dagdagan yung registers natin para mabilis lahat, di ba? Store na lang natin sa registers yung memory. So we can't do that kasi registers are very expensive to manufacture and build. Kasi yun nga, merong mas mabilis na timing requirement sa registers. So mas maganda or mas designed sila to be parang high power, very, very fast. Pero ayun, if ginawa natin puro registers yung laman ng ating computers, baka masyado na siyang mahal. And hindi tayo makakabiling computer kasi mahal. Anyway, after makuha ng instruction, kailangan nating i-decode or anong ibig sabihin ng instruction na yon. So that is number 2. The next step is, ayun, pag alam mo na kung ano yung kailangan gawin ng instruction, kunin na natin yung mga operands. So ano yung, kung add yung operation, ano yung mga ina-add natin. Kung pag sinabi natin kung ano yung action na i-add. So if for example sa instruction sinabi si T0, i-add ko kay T1, by step 3 is ina-add ko na yung, alam ko na dapat yung contents ni T0 and ni T1 and ina-add ko na sila in step 3. And then, ayun, actually yung pala yung sa step 4. So sa step 3 is parang kinukuha mo na yung mga operands mo from kung ano dito sa register file. And sa step 4, doon pa lang pala tayo mag-add dito sa arithmetic and logic unit na tinatawag natin. And then after nun is store yung result either sa memory or sa balik sa register. Ayan. So ito yung mga parang building blocks na ating data path. Kung medyo tumahimik na nangalay na. So, ayan. What's next here is, ayan, instruction memory, laman ng instructions, register files, yung ating registers. ALU, arithmetic and logic unit, so siya yung gumagawa ng actual na addition, yung actual na subtraction, or yung shift. So ganyan yung mga possible implementations niya. Meron siyang add block, meron siyang OR block, meron siyang shift block. Tapos naka-multiplexer yung result niya depending doon sa ALU operation. So ito yung medyo simple na data path if you want to support add, subtract, and or operations. So ayun, meron tayong PC na tinatawag or program counter kung ano yung current address ng instruction. So ayun, magsa-start siya sa 000. And yung code, so kung ito yung equivalent niya in yung MIPS instruction niya, ito yung equivalent na code niya, yun yung makukuha natin from this instruction memory. Tapos hihimayin siya nung ating data path. So yung first 6 is mapupunta dito kay instruction code. So pumupunta siya sa control unit na hindi nakalagay dito sa slide. And then yun, so yung bits 21 to 25 siya si RS, si 26 to 20 siya si RT, and is 11 to 15 siya si RD. So papasok sila sa register file na yan. So ito yung sa step 1, pagbabasa sa memory. Step 2, yung decoding. And then step 3 dito, lalabas na yung data na pinasok natin sa address or yung sa read reg dito. And ayun, lalabas sila dito papunta sa ALU natin. And then itong instruction, itong write enable at saka yung ALU operation, lahat ng control signals na yan galing siya sa controller natin. And then ayun. Manggaling siya sa controller natin and magbe-based yung laman ng mga yan depende doon sa pag-decode ng instruction. So parang merong part nung pag-decode na wala dito and nandun siya sa control unit. So, ayun, after yung result is, dito is i-write back nyo lang sa register file kasi yung puro R-type instructions pa lang naman. Now, paano mag-move on dun sa next na memory? Actually, nilalagyan lang ng adder ng 4 para pumunta siya dun sa next na address. So, ayun, para pagka-increment niya or sa next cycle, pag next time na matrigger yung flip-flop na to or yung register na to, is mag-update yung value niya. So, yan, yung control unit, siya yung nagde-decide kung ano yung mga signals nitong instruction, itong write register file at saka ALU off na flag. So, basically yun, yan yung pag-add, subtract, and OR. So, yung mga operations na yan, approximately nasa loob lang sila ng ALU. So, kung gusto natin magdagdag ng iba pang instructions, ayan, dumadagdag na. Pag may immediate, meron tayong sign extend para pag nag-add tayo, 32 bits. Sila pareho. So, ayan, so yung 32-bit extended na immediate, siya yung papasok dito tapos magdadagdag tayo ng multiplexer para mamili kung saan siya isusulat. And since ayun, si RT pwede siyang maging second register or yung right register, may multiplexer tayo ulit dito. So the more instructions na i-add mo, mas nagiging complicated yung data path. And then ito yung summary din ng mga instructions or nung control signals natin per operation. So, parang ayan. Kaya nyo dapat intindihin. If may mga questions kayo, just let me know. Since unfortunately, wala yata makaka-attend ngayon, I guess kailangan ko hintayin yung messages nyo para masagot sila. So yan, ayun sa single cycle. Now, bakit natin gusto mag-multi-cycle? Since ang isa sa mga motivations bakit ka mag-multi-cycle is that hindi naman lahat ng instructions dadaan sa lahat ng to. So pwedeng nagkaroon ng data memory. If hindi naman natin kailangan magsulat sa data memory, pwede tayong dumiretso sa register file. So parang may kita ba dito? Yeah. I think ito. So merong mga delays kasi doon sa ating data path. So ayun, depende dun sa mga delays ng lahat ng kailangan daanan, siya yung nagde-determine ng ating clock frequency. So kung ano man yung pinakamahaba, kailangan i-accommodate ng lahat yun. So for example, meron tayong instruction na kayang matapos na dumaan lang sa PC, sa reg file, sa insmem, tapos after ng ALU, write back agad dito. Pero meron din tayong instruction na kailangan dumaan sa lahat. Hindi,
ang nangyayari doon is kailangan natin iset yung clock frequency natin to accommodate yung pinakamabagal. So parang kung sino yung weakest link doon sa instruction, siya yung nagsiset noong ating instruction frequency. So ang gustong gawin dito, and so parang may legend dito. So yung IM is instruction memory, RF is register file, ALU, data memory, tsaka address computation. So pag nag-add operations tayo, kailangan lang natin si instruction memory, register file, at tsaka si ALU. Pag nag-load word tayo, kailangan natin si IM, si register file, si ALU, at tsaka si data memory. Pag nag-jump naman tayo, yung instruction memory lang at tsaka yung address computation na yung kailangan. So, kahit si jump, 100 nanoseconds na yung kailangan niya, yung clock period natin, kailangan mag-adjust dun sa pinakamahaba, which is 60 plus 40 plus 50, 60. So, gano'n. So, kahit, excuse me, siguro if meron kang program na puro J yung operations, pero meron kang isang load word na operation, kailangan lahat ng instructions mo 160 nanoseconds per clock cycle. So parang instead na 100 nanoseconds per instruction na lang if puro J, since nagdagdag ka ng isang load word na instruction, lahat ng J instructions na yan ay 100 nanoseconds. So parang pinapabagal niya yung buong thing or yung buong operation. So, ayun, yun din naman ang sinasabi dito. So, for a multi-cycle operation, so yun, since kaya nating i-section yung ating pag-operate, pwedeng sabihin na lang natin, kailangan natin ng 3 cycle para dito, kailangan ng 4 na cycle para dito, 2 cycle para dito, para maging variable yung instruction time natin. So, ayun, so since dito si load word 210 pala siya. Lahat ng instructions magiging 210. So yung 3 clock cycles natin is 630 nanoseconds. Ngayon kung yung longest na operation or yung longest na sub-operation yung take note natin, what is si IM60. So yung IM, RF, tsaka ALU tig 60. Tapos ito, tig 60 rin yung mga to, tig 60 din yung mga to. Since ito, may nawalang parts dito, so mababawasan yung number of clock cycles nila. And then, ayun, so yung total number of clock cycles dito natin, 9. 9 times 60 is 540 nanoseconds. So, pag from yung single cycle na 630 nanoseconds, pag nag-multi-cycle tayo, 540 nanoseconds na siya. So, ang mangyayari lang dito is, ayun, ang disadvantage lang nito is what if lahat sila kailangan gumamit ng 4 na clock cycle each, edi humahaba siya. Pero pagka, yun nga, pag puro add instructions ka lang, umiikli siya. And ayun, so yung pahirapan na lang dito is pag-implement sa kanya. So parang sinisection natin yung ating data path dito sa mga parang major parts na to. And this is actually yung 5 parts ng instruction execution here, which is yung fetch, decode, operands, and then store result, tsaka yung perform operation. So halos ito lang din yun. So si IM, RF, ALU, DM, at tsaka si AD. Although yun nga, may additional yata dito si DM, and si yung decode at saka register file access is may pag-isa sa isang cycle. So kung titingnan mo dito, yung first cycle, ang makikita mo dito yung mga cycles natin is determine kung nasaan yung mga registers natin sa ating data path. So yung first cycle is from PC to IR. So yun yung instruction fetch. Yung next register natin is from IR to D. So ito yung kasama yung sa decoding at saka yung pag-fetch ng register values natin. After naman ito is from yung decoded na registers to yung output ng ALU. And then after naman ito is from yung ALU to the memory register. So, or either, ayan si ALU, either pumunta siya kay memory register or pumunta siya kay write data. So, itong diretsong loopback na to is pagka magsusulat ka lang sa register. Ito naman, pupunta ka sa data memory, tapos papasok ka sa memory register, tapos pupunta ka pa sa write data. Pagka meron tayong nag-shift or yung load word at saka save word na instructions. Kaya sila yung usually mahaba. Excuse me. And then, dito rin meron din parang bypass or diretso sa data memory if hindi kailangan dumaan ng ALU. So yun, nagpapakomplicate din dito yung mga control signals. Pero most likely than not, yung mga control signals natin is halos same lang naman dito. Pero yun nga lang, meron tayong added complexity nung per clock cycle. So, ayan, so parang iba-iba na yung per clock cycle, iba-iba yung instructions na kailangan natin galawin. Now, tapos ito yung sa controller naman, yung since hindi lahat ng instructions pare-pareho yung number of clock cycles, so parang gumagawa tayo ng state machine. So for all instructions, first same yung dalawang first two instructions. So yung for all instructions, same yung first two cycles na ginagawa. So that is yung instruction fetch at saka yung pag-decode dun sa register file. So nag-iiba-iba sila dun sa third cycle. So, kung ito, ano ba? Yung parang base natin dito is yung R-type na instruction. Na yung first one is yung instruction fetch, instruction decode, and then dito yung ALU result, tapos R4 yung write back. So, ito yung main. And then, for the branch operations, same yung 1 and 2, pero sa cycle 3, doon nagkakaroon ng branch. So, ayun. And then sa save word at saka load word, sila yung mahaba dito. Yun. Actually, si load word yung pinakamahaba. Dadaan siya ng E1, E2, I3, L4, tsaka L5. Tapos, ayan. Basically, yan lang din naman. Parang guide lang siya to determine yung control signals. So, kada state dyan, meron silang corresponding na control signals dyan. Okay, so yung next naman dito is yung pag-transition from multi-cycle to pipeline na data path. So, since nag-move tayo to a multi-cycle na structured data path, pwede mo isipin na para siyang gumagawa ka ng laundry. So, parati itong example. So, pag nag-laundry ka is yung first is isa-soak mo yata sila and then lalagay sa washing machine tapos i-dry tapos lalagay sa cabinet. So, parang ang point dito is per step of the laundry cycle, isang device yung ginagamit mo. Pag ginagamit mo na yung washing machine, yung yung sink hindi mo nagagamit, pero pag nagda-dry ka na ng damit, hindi mo nagagamit yung washing machine. Pag tinatago mo yung damit sa cabinet, hindi mo nagagamit yung pang dryer mo. So, ang gusto natin gawin sa pipeline is after gamitin ni first person yung sink, pwede niya nang ipasa sa second person. Habang si first person is doon na siya sa washing machine. Tapos, so basically since yung mga parts natin hindi 100% na i-utilize, after gamitin ng first instruction yung first device, is pwede siyang gamitin ng second device kahit hindi pa tapos yung first instruction. So, Ang mangyayari dito, after every cycle, basta puno yung pipeline, may isang natatapos na instruction per cycle. Compared dito, every 4 cycles, tsaka pa lang may matatapos na isa. So parang ito, from 6 a.m. to 12 a.m., tatlo yung nakapaglaba. Pero dito, from 6 a.m. to 9 p.m., tatlo rin yung nakapaglaba dahil nag-pipeline tayo. So medyo same lang naman yung kanyang control, almost entirely the same, yung control niya with the multi-cycle na data path. Although yung difference kasi dito is pwede tayong magkaroon ng tinatawag na hazards, which causes the pipeline to deviate from its ideal behavior. Pero before dito, I think merong mga metrics na diniscuss dito. So, ayun. So, parang yung per instruction natin, kaya natin silang i-separate into 5 different na 5 different steps. Ayan. So, instruction fetch, instruction decode, ALU execution, memory access, and write back. So, yung single cycle natin, let's say ganyan siya. And then yung 5-stage pipeline is ganyan siya. So, ayun. So, if each instruction dito natatapos in 5 nanoseconds, one instruction per 5 nanoseconds. Dito, if ang ating instruction ay 5 nanoseconds each, kailangan lang ng every 1 nanosecond may natatapos na instruction. So, yung speed up natin is, if i-compare mo yung speed before sa speed ngayon, so yung speed natin ngayon, 1 instruction per 5 nanoseconds, compared it to 1 instruction per 5 nanoseconds is speed up of 5. Although yun yung ideal, although meron tayong mga non-idealities. So for example, if yung cycles natin look like this, if hindi pantay-pantay yung hati, magdedepende yung ating clock cycle doon sa pinakamalaki. So similar siya sa multi-cycle na data path. So if 2 nanoseconds yung pinakamalaki dito, per cycle natin is 2 nanoseconds. So ang speed up natin instead of 5 is magiging 2 na lang. Pero improvement pa rin naman. Diba? So to compute for the CPU time is for an X stage na pipeline is, ayun, meron X minus 1 cycles para doon mapuno yung pipeline plus yung actual number of instructions. And then if gusto mong makompute yung CPU time is yung number of cycles yung number of cycles nung ito yung number of cycles times yung period or yung divided by the rate ng CPU. So, ayun. So, ideally, itong pipeline, yung additional steps to fill up the pipeline, hindi masyadong na-matter. For example, malaking-malaki yung number of instructions, proportional na yung number of instructions sa number of cycles, or parang almost equal na sila. So, yung CPU time natin is parang instruction times yung clock frequency natin, or yung instruction times yung clock period or divided by the clock frequency. So, yun. So, paano natin ipa-pipeline yung ating data path is basically isa-section mo siya based dun sa mga ating mga operations. So, meron tayong pipeline register in between yung instruction fetch at saka instruction decode. May register between instruction decode and execution, and then execution memory at saka write back. So, meron na pipeline registers na. So, ano yung tinatawag nating hazards is, ayun, di ba sa pipeline, meron tayong parang 1, 2, 3, 4, 5 na sections. Eh, what if yung instruction natin kailangan niya yung yung gamit dito sa kabilang part ng pipeline. So, yun yung tawag na structure hazards. Since merong resource na ginagamit and hindi siya magagamit ng... So, parang kanya-kanya yung mga pipeline stages natin. Dapat sa isang pipeline stage is wala siyang kailangan from the other stages. So, dapat strong and independent sila. So, if ever kasi, lalo na if nagta-transition ka from multi-cycle to pipeline, baka meron ka kasi mga shared na hardware and yun yung isang potential na hazards doon. Then, next dito, ayun, so yung simple example dito is pag naka von Neumann architecture ka, yung memory mo for data at saka memory mo for instruction, pareho lang. So, in that case is, meron kang structural hazard. So, data hazard naman is yung much more common. So, for example, ang first instruction natin dito is load word kay R1. Pero yung next instruction natin, kailangan na natin yung result ni R1. Kaso yung instruction decoding natin, which is where kinukuha natin yung result ni R1, nag-occur siya before magka-write back si load word. So yung state ni R1 at cycle 3, hindi pa siya na-update. So hindi pa siya tama. So that is what we call a data hazard. So ano yung pwedeng gawin para maiwasan ng data hazard? Meron ba dito? Wala. Yung control hazard muna, siguro, ayun. So yun yung data hazard. So paano siya solusyonan later on sa slide set. Then sa control hazard naman, ayun, similarly, meron tayong branch operation. Parang 5 cycles pa talaga siya before matapos. Pero pag natapos siya, yung nakastore sa pipeline natin, what if kailangan natin mag-skip dito? So, sino yung ilalagay natin dito sino yung ilalagay natin sa pipeline? Yung pupuntahan ng branch or kung ano na lang yung kasunod niya? So, parang either way, lugi ka. Kasi what if yung other one siya? So, ano yung gagawin natin when we have these hazards through software? So, yung first natin na pwedeng gawin is mag-reorder ng instructions. So, ito, bago mo gamitin si R1, maglagay ka muna ng siguro, I think, 2 or 3 instructions bago mo siya ma-access. Bago mo siya i-access ulit. So, yun yung pag-reorder. Or yung similarly, pwede kang maglagay ng no operation. So, parang 5 cycles siya walang gagawin. Then, ayun. Instruction ng paglalagay ng no dun sa kanina. So, si load word maglagay ng 3 no operation para pagkatapos ng write back, tsaka pa lang magsa-start yung yung instruction decode ni BQ. Tapos, ayun, si BQ, since here siya, after 2 instructions mo pa malalaman kung sino yung pupuntahan mo. So, after 2 instructions ka pa lang mag-ano sa pipeline ng instruction. So, another, so ito yung mga pwede mong gawin in software. Yung mga pwede mong gawin in hardware is stalling. So, para siyang no operation pero hardware siya ini-implement. Another is yung branching. Forwarding po na pala. Pag forwarding, ang gagawin niya is, for example, after naman ng execution, meron ka na nung tamang result ni R1. Ang problem mo lang is hindi siya nakasulat pa dun sa register. So, ang gagawin mo, gagawa ka ng path from execution stage nito and siya yung itatap ng execution stage ng susunod na stage. So, basically, hindi pa tapos si instruction 1, pero may sagot ka na dun sa result niya. Hindi mo pa nasusulat in memory, pero pwede mo nang gamitin dun sa susunod na operation. So, ayun. So, usually yun, naglalagay ng forwarding path between yung XMM ng naunang stage doon between sa ID XN nito or sa between sa mem and write back. Then, ayun, more examples of forwarding. If not, kung ito kailangan ng R1, si R1, finorward mo na siya kay dito sa second instruction, and then pwede mo rin siyang i-forward dun sa third instruction. Tapos, dito rin sa fourth instruction, pwede mo rin siyang i-forward. Pero pag finorward mo siya to the fourth instruction, is hindi ka pwedeng kumuha dun sa write back. Pero, well, naka-write back ka naman na. So, wala namang hazard dito. So, hindi mo na kailangan. Hindi mo na kailangan gawin ito. So, usually, ang ginagawa naman dito nasa same cycle or nasa same line sila. Ayan. So, ito, other examples lang din. Ayan, tapos sa branch prediction, ayan, predict natin kung sino yung pupuntahan. If mali, if a flush, so i-discard lang. So, parang effectively nagiging nope yung ano. So, yeah, yung simplest approach is assume na hindi ma-take yung branch. So, parang tuloy lang yung pag-execute mo. So, dito yung branch operation. Tuloy lang yung pag-execute. And then, if nalaman mo na tama yung nagawa mo, edi yun, nakatipid ka. Pero pag hindi, ipa-flush mo. And then, mag-move on ka sa next na instruction. So, ayun lang. So, hindi siya perfect, of course. Parang nahati mo na lang yung times na kailangan mong wait. So, yeah. Or yun, other approach, assume branch taken. So, yeah. So, yung major problem mo lang sa pipelining is yung hazards. And actually, yun yung main coverage ng mga extra questions dito. For example, dito si question 5, consider a 5-stage MIPS pipeline data path fed with the instructions above. And then yung forwarding na kailangan natin is between yung first instruction and yung third na instruction. So yung data path natin is ito, medyo simplified form siya. So ayun lang, take note lang din. So kahit MIPS yung pinapresent, meron silang slight variations. So always double check your given kung pare-pareho sila and then make adjustments accordingly. So dito ang first question is to enable forwarding to the ALU ng execution stage dito, mag-add tayo ng multiplexer. Tapos, ayun. So ang first question is the signal that must be connected as the default ALU input is ito yung mga choices. So, default na ALU na papasok is yung mga ID/exe na reg data, either 1 or 2. So, since dito sa question is si operand A, so siya si reg data 1. So, reg data 1. Next question is, based dun sa above, ang signal na kailangan natin i-forward to the ALU must come from dito, sa gitna ni memory at ni write back. So, sa gitna ni memory at saka write back, siya yung i-forward natin to the ALU. And yung i-forward natin is yung result ng ALU output. So, between yung memory and write back, ALU output. And yung option na to is yung isa-select ng multiplexer pagka yung destination ni instruction na nasa mem write back stage is pareho siya doon sa source no nasa IDEXE stage. So, ayun. So, yung nasa mem write back stage, yung destination doon, kailangan pag-equal siya doon sa IDEXE reg source, yun yung yun yung time na magfo-forward tayo ng data. So, ito naman ibang instruction. So, ano dito yung kailangan nating i-forward? So, ito ang result niya si R3, yung first instruction. So, hindi siya kailangan at all. And then, So yung may kailangan lang dito is yung sa second instruction, si R1 is forwarded kay third instruction. So kailangan natin i-forward yung result. Kailangan natin ma-forward sa third instruction dito sa execution yung result ng previous, which is dito natin kukunin. So yung previous kanina is since may one instruction between sila, ang kinukuha natin ng signal is yung between mem and write back. Pero in this case, since magkasunod sila, kukuha tayo doon sa between exe and mem. So yeah. So between exe and mem na ALU out. So select natin to pag si exe mem na source ay exe mem na destination equal siya dun sa source ni ID exe. So exe mem na destination ID exe na source. Then, ayun, another sequence. So, makikita natin dito is si R1, sinulatan siya dito, gagamitin siya dito, and then gagamitin siya ulit dito. So, may dalawang options. Tatry mong, since kung in-implement mo yung pag-forward dito at saka yung pag-forward dito, sa nauna, basically, pwede kang yung exe stage nito, pwede mong itap si exe mem or pwede mong itap si mem or mem write back na ALU out. So, ang question is, alin dapat dun yung kukunin natin? So, of course, since ang nangyari kasi dito sa first na instruction natin, supposedly nag-forward na tayo dito sa kanya dito. So yung result nito hindi na natin kailangan i-forward pa. So although ayun, pwede mo rin i-forward din, pero since pareho silang ng value, mas updated si R1. So ang kailangan nating isulat dito is yung C galing kay XML register. So yun lang naman dito for medyo mahaba-habang question 5. Then dito sa next question, and suppose the instructions below are executed in the 5-stage pipeline na pinakita previously, and then assuming the data path does not support forwarding or stalling. So yung first question, which among the load word instructions may not execute as intended, or in other words, alin dito yung merong hazard. So a good approach to this is sulat natin yung pipeline nila. So ayan, medyo lakihan lang natin through the magic of editing. So yeah, for instruction merong IFID, XMM at saka WB. So which among the load word instructions may not execute as intended? So looking at yung mga load word na instructions, lahat sila kailangan nila yung value ni R5. So yung possible source natin ng hazard is yung first instruction na R5 papunta sa kanila. So ayan, so looking at yung ating pipeline dito, kailangan yung result ng write back available na sila sa instruction decode nito, ni instruction 3, instruction 4, at saka ni instruction 5. So looking at this, ang tumama lang na on time na may write back before ID is si instruction number 5 na load word. So ang may data hazard natin is si instructions 3 and 4. So similar yung next question, pero this time dun sa add na operations. So una tingnan natin itong instruction 6 na i-add nga si R1 at saka si R2. So ibig sabihin nun, si instruction 3 kailangan may maging ready na siya by this time bago mag-instruction decode, and pati si instruction 4 dapat tapos na siya before mag-instruction decode. So even if we're assuming na walang hazard na nangyari dito kay 3 and 4, hindi pa rin sila on time na dumating. Although another consideration nga, since si instruction 3 and si instruction 4 may hazard na sila, edi yung gumagamit ng result ng instruction to yung instruction 4, hazard na rin siya. So, ayun, so meron tayong 2 reasons, so more. So for sure, hazard na siya. So next naman dito, ayun, actually since hazard na si R7, or hindi na tayo sure kay R7, hindi na rin tayo sure kay R7 dito. So, yun pa lang, pwede na natin siyang i-assume na hindi siya gagana as intended. Pero looking at yung timing din natin, yung write back ni 5 and 6 is malayo pa doon sa instruction decode ni instruction 7. So lahat, so both add na operation 6 and 7 ay hindi natin ina-expect mag-execute ng tama. So to remove the very first hazard, which is kay instruction 3, kailangan natin insert ng no operation. So paano natin malalaman kung gaano natin siya kalaki i-shift? So gusto natin yung write back nito is yung sa start ng information decode nito. So ayan. So yung write back, kailangan nandun siya sa before no instruction decode ni instruction 3. And to do that is kailangan natin magdagdag ng dalawang no operation. And kailangan before instruction 3. So dalawang nops before instruction 3. Now, so kung ano nalagay mo na nga yung nop dito, saan yung next hazard natin? Sa instruction number 6. So, itong hazard na to. So, since nasolve na natin yung hazard kay instruction 3, for sure, solve na rin yung hazard kay instruction 4. So, yung next hazard natin kailangan i-account is si instruction 6. So, similarly, kailangan natin itapat yung write back doon sa ID nung 6. And of course, kailangan natin i-take into account yung latest na write back na kailangan, which is from instruction number 4. So in this case, dalawang nop lang din yung kailangan para mapuno yung table. And ayun, so dalawang nop operation before instruction 6. Okay. Last question. In a single cycle data path, actually dalawa pa pala to. Ito is just true or false. So consider the statements below, and ayun, which among these are false? So, pwede naman natin. So in a single cycle data path, while the instruction at address 4 is being executed, the PC contains a value of 4. So single cycle, so while it is being executed, 4 pa rin dapat yung naman yan, di ba? So, 3. In executing an R-type instruction, the write register file signal must be asserted on the last clock cycle of the execution and don't care otherwise. So, R-type instruction. So, don't care ba siya otherwise? Well, generally, pag meron tayong write na signal, usually, meron tayong care kung 1 or 0 siya. Kasi we might accidentally write or overwrite data. So, hindi siya. So, itong part na to is yung main way kung bakit siya, or yung main reason natin bakit siya false. So, a single cycle data path can be pipelined directly without designing a multi-cycle data path. Although, ayun, ang keyword dito is can. So, of course, para makagawa ng pipeline, maganda if meron tayong multi-cycle na data path kasi halos pareho na lang yung control signals natin noon pag transition natin. Although, hindi naman talaga siya necessary. Pwede naman from the single cycle data path natin, pwede tayong pumunta directly dun sa pipeline. So, since can lang naman yung tanong, hindi naman suggestion, this is already. And then number 4, pipeline registers between stages of a pipeline data path may be composed of different number of registers. So that is true. I think meron sa example dito, yung data path natin. Ayun, meron tayong extrang register dito sa pipeline na to, and itong mga registers na to, wala sila dito. So, of course, parang obvious naman na pwede nga silang iba-ibang numbers. And draw. Then lastly, in a pipeline data path, not all control signals are generated in the control unit in the information decode stage. Ayun. So, dun sa pipeline na data path natin, so sa information decode, this is here. So, well, of course, meron tayong mga control signals na dito lang kailangan, dito lang kailangan, dito lang kailangan. So, hindi naman talaga lahat kailangan asserted sa ID stage. So, medyo straightforward na. So, yan. Actually, number 2 lang pala yung false. So, yun. And then, last one. May konting computations. So you are given two versions of a program, V1 and V2, that essentially does the same function. Regardless of which is chosen, the program will be run at a multi-cycle with a multi-cycle processor that runs at 50 megahertz. So yung load word instructions daw ay 4 clock cycles. Ang store word 3, ang branch ay 4, and yung other instructions ay 3. So, ayun. So suppose V1 and V2 need to execute the following number of instructions dito. So how many clock cycles are needed to finish V1? So kailangan lang natin mag-summarize, or parang summary lang, pag i-add, isa-sum up lang pala natin sila. So 4 clock cycles sa load word, 3 sa save word, 4 sa branch, 3 times sa others. So yan, plug and play lang. So for V1, 4 times 50, 3 times 50, 4 times 100, 3 times 150. Ay, nangyari. May share screen. Okay. And tapos total mo lang. Tapos gamit ang mental ma. Ang sagot ay 1200. And then what is the effective CPI for the data path in this case? So ang CPI ay cycles per instruction. So meron tayong 1200 clock cycles for a total of 350 instructions. So 1200 over 350, 3.43. So ganun na siya kadali. Parang reading comprehension lang talaga. And then ayun, for V2, same. Ayun, imbis na 50, 25, 25, 50, 300, and you'll get 1275. And then ayun, so yung effective CPI, 1275 over 400. Ayun. So what is the worst case speed up when shifting from one version to another? So basically, compare lang natin yung CPU or execution time nilang dalawa. So si execution time ng first one is yung cycles ni V1 over 50 megahertz, and then yung cycles ni V2 over 50 megahertz. So 1200 over 1275, which is 0.94118. So worst case, kasi siya yung smaller na speed up. Kasi pwedeng ito yung speed up ni V1 over V2, 0.94. Pero pag kinuha mo yung speed up ni V2 over V1, inverse niyan, mas malaking speed up siya. So it's the better case. So ito yung worst case. So ito yung medyo spicy na tanong. The program V2 is run on a 3-stage pipeline where each branch requires 1 clock cycle to stall, while 60% of the load words required, necessitated, kinailangan, 1 clock cycle of stall to mitigate data hazards. How many clock cycles will be needed by this pipeline, including yung clock cycles needed at the start to fill the pipeline? So, ang total number of instructions natin pag pipeline is yun na rin yung total number of cycles. So, ang total number of instructions natin is 400 and idadagdag na lang natin yung para sa stall. So, yung stall for the branch at saka stall for the load word. So, yung stall for the branch is equal lang siya dun sa number of branches. And then yung stall for the load word is 0.6 times yung sa load word. So, 400 plus yung branches, which is 50, plus 60% ng load words, which is 25, we have a total of 465 instructions. And then, yun nga sa pipeline, ang total cycles natin is 1 cycle per instruction lang tayo, plus stages minus 1. Ano yung stages minus 1? So, siya yung clock cycles needed to fill the pipeline. So, stages minus 1 is 3 minus 1, 465 plus 2, 467. So, ayun. So, regardless dun sa unang given na 4 per load word, 3 for store word, and 3 for other instructions, pag pumunta tayo to a pipeline na data path, hindi na nagmamatter yon. Kailangan na lang natin yung total instructions. Since yung total instructions natin dumagdag dahil doon sa mga stall para sa branch at saka sa load word, idadagdag lang natin yung dun sa count. And ayun, kaya punta sa 465 plus yung pag-fill up ng pipeline, which is yung number of stages, 3 minus 1. So yun. So yun lang yung aking mga pin-prepare na questions. Then, gusto ko lang din i-share na sa UVLE, sa week 4, meron mga sample problems na provided. And this is, I would say, very, very helpful. Sana you can take the time to go over it. So, since medyo wala ng time, hindi ko na siya mako-cover. Pero yan, ito yung mga common na questions din is kung ano yung mga control signals per cycle or per, and so for a multi-cycle, ano yung mga control signals per operation per cycle. So, note lang here, I think iba yung data path na ginamit, comparing it to yung single cycle data path dito. Ayun. So, ito isang ALU lang siya and walang data memory. And then, dito naman, meron tayong additional na other dito, I think for branch operations na hindi existent dito. So, kailangan mong mag-modify ng konting data, ng konting signals to accommodate that change. So, ayun lang. I guess I'll end here. And nag-join. And naka-record naman ako. And ayun, I guess I'll end here. If you have any questions, direct message, email, and ayun. See you.